Good evening, everyone, and this is your host Anant, and welcome back to another video. So, in the last video, what we learned was what was it? It was about graphs. So, we learned what graphs are. It is nothing but a non-linear data structure to simplify storing the data around us. Suppose in the last video, I forgot to give examples. So, let's just discuss one example here. An example could be if you are to store the paths that are connecting the different locations in a city, that will be a problematic task if we were to do it using some other data structure. But through a graph, it becomes very easy. We can simply store the locations as vertices in the graph, and the edges will represent the paths that take us from one location to another. So that's an use case of graph, Google Maps. Okay, so in today's video, what we'll be doing is like, let me just tell you a spoiler. um, I just ended recording this video, and what happened was that recording didn't start, and I completed the whole lecture. And after that, I'm realizing that I haven't even started the recording. So that was so silly of me, and that's why you see this graph already drawn here and this matrix written here. So it's good for you guys, like, but I just had to record it twice. So otherwise, I would have come up with a blank word, like in the last video. Like, I have written something here just to brief you, like, so that I don't have to write it again and again here. That will waste your time as well. So let's just come to the point. The point is, in the last video, we drew graphs like this. So we can't logically represent graphs like this in a computer system or in a program. So what we do is we have two primary methods to represent graphs. The first one being an adjacency matrix, as you can see drawn here, and the other one is an adjacency list. That's tough to pronounce. Whoever agrees with me can comment in the comment section. That's not just like, keep it simple. Okay, so what exactly is an adjacency matrix? So we all have worked with 2D arrays. So an adjacency matrix is nothing but a 2D array used to represent the connections between the vertices. Like, we'll be storing the edges in this matrix. So what we do is, like, we have a graph here with four vertex, and we'll be creating a matrix of the size n plus 1, where n represents the order of vertices. Okay, the number of vertex. Okay, so we have created an array here. Why 1 extra? Because arrays are zero index, and in most of the cases in problems where we have to use graphs, we have the count starting from 1. So that's why we have done this. Okay, so what we do in adjacency matrix, we take this vertex. This is 1, so we go here 1. Okay, and we see what all vertices it is connected to. 1 is connected to 2, 3, and 7. So in the ones row, we'll be marking 1 is not connected to itself, so we'll not be marking it. 3, 2, and 7, we'll mark these, and simultaneously we'll be marking one's column in all these rows. 3 is connected to 1, 2 is connected to 1, and 7 is connected to 1. Similarly, we'll be repeating this process for every vertex. So for 3, we'll be looking 3 is connected to 7. This is an undirected graph. That's why we are marking the edges simultaneously. If it were to be a directed graph, then we'd have marked only row entries. Okay, so similarly we can do it for all the vertices. And now let's just have a look at how we can do it in the code. Like, we should just have a brief of what the code looks like. So I just have the code here. Okay, so n is the number of nodes or vertices, m is the number of edges, total number of edges. So we have a vector of vector, a 2D matrix basically, initialized with n plus 1, and it initialized with 0. Okay, so we'll be iterating through all the edges, and we'll be taking the edge inputs. Then we'll be simultaneously marking both these entries in the matrix. This will do our job. If it were to be a directed graph, then we'll slash off this line, and our task would be done. And the other way to represent a graph is using an adjacency list. For each node, store a list of its neighbors. This is what we have done here. So this will be like, in practice, it is done using a linked list. We basically create a list, an array of node pointers, head pointers, 0, 1, 3, 2, 7, the total number of nodes we have. We create an array of nodes, linked nodes, and then we keep attaching these. We keep storing this the vertices this node is connected to. So in this case, we had to mark those entries, and in this case we'll be appending those entries into the array or linked list. Linked list is more better, like insertion and deletion is faster than linked list. So that's how we do it using an adjacency list. Like, see, 1 is connected to 2, 3, and 7. So we put 3, 2, and 7 in front of 1. We appended 3, 2, and 7 in front of 1. Similarly for 3 is connected to 1, 7, and 2. So we appended 1, 2, and 7 in front of 3. And similarly for 2 and 7 we have done. Okay, so let's just discuss about when to use the first one, adjacency matrix, and when to use the adjacency list. So if we have, like in the last video we discussed sparse matrices and dense sparse graphs and dense graphs. So if we have a sparse graph, which one out of these two do you think is preferable? Let me just answer it. Okay, so in that case, using an adjacency list would be preferable, because that will save us a huge amount of space, because we don't have many number of connections, and using an adjacency matrix would simply waste off space. So in such cases where we have sparse graph, we should prefer using an adjacency list. And in the other case, when we have a dense graph, we should prefer using an adjacency matrix. That's as simple as it gets. Okay, so now is there any we have very fast lookup here, and rest other operations are similar for both the cases. Let's just have a look at the code for the second one. So we have a vector of vector here. Like, instead of having it int, you're simply storing the connection, so we can have the data as well. Otherwise, if we were storing the address, then it could have been linked node as well. So that's as simple as it is. So we iterate through the number of edges, taking the input bit of the vertices between which this edge exists. So, and finally in the vector of u, we'll be pushing back v, and in the vector of v, we'll be pushing back u. So that will do our job, and that's how you represent graphs using adjacency matrix and adjacency list. If you have any doubt, you may post it out in the comment section, and we'll meet each other in the next video. Till then, bye bye guys. And if I did any mistake throughout the lecture, please post it in the comments. I'll be very happy to learn about those and improve.